calculator often enough, you'll have run into something like this before. Now, how do these logarithms work? And what exactly do they do? Well, let me talk to you about what this is. This is the logarithm base A. That little a there next to the log is the base of our logarithm. Just like these exponentials have base A, logarithms have bases as well. Those bases have a connection between them. If I write log base A of x equals y, what that means, how to interpret this in terms of what we're saying, this is the same thing as saying a to the y power is equal to x. That's the connection that we have between logarithms and exponential functions. This connection right here. So as an example, log base 2 of 8 is equal to 3. Why? Why does this make sense?
2 to the 30 equals 8.
Because if we write this as an exponential, 2 to the third power is in fact 8. So these logarithms are just a fancy way of telling us how many exponents we need to write the number in parentheses as this base to that many powers. Being able to go back and forth between these different things is a useful tool. It allows us to sort of simplify working with these logarithms into maybe something that we're more familiar with, which is exponential functions. Okay. All right, so great. We now know that inverses of exponential functions are logarithms. Let's take a look at some graphs of logarithms for a moment. There are two types of graphs we want to look at. Okay, so we'll do the first one over here. Let's take a look at the function y equals 10 to the x. Okay. There's our graph of y equals 10 to the x. All right. What is the inverse of y equals 10 to the x? Well, we go back and look at this stuff we have over here. The inverse of 10 to the x is going to be log base 10 of x. These are inverses of each other. Again, if you go down and plug them into this relationship here, you'll see that 10 to the y equals x. Well, that's exactly the opposite if we switch the variables over here of what we get. All right, so this is the inverse. What is the graph of this thing going to look like? Now, we talked a little bit last time about the relationships between graphs of functions and their inverses. We said that if we reflect it over that line, we sort of folded our graph over that line, the thing that came out would be the graph of the inverse function. Okay. So the graph of this function, if I sort of follow those rules, should give me something that looks like that. Okay. And this is what the graph of y equals log base 10 of x looks like. All right. Let's talk about the domain of this function. What values can I plug into the log function? We talked about these relationships last time. What values can I plug in to this function right here? Okay. If we go back and think about the relationship between the inverses, the inputs here are the output values I get from this function, right? When I raise a positive number to any power, do I ever get a negative number out? No. I'll never get a negative number out when I raise a positive number to any power. Will I ever get 0 out? I'll never get 0 out. I can get as close to 0 as I want, I'll never actually get 0. And so in this case, my domain here has to be greater than 0. Now, obviously, these exponential functions can get as large as I want them to. So I get from 0 all the way out as my domain here. Okay. Remember, this is the range of my original function. 0 to infinity is the range of my y equals 10 to the x. All right, let's talk about the range of this logarithm function. What numbers can I plug in? Or what numbers can I get out of this log base 10 function? Okay. If we look at what's going on here, as sort of the graph is telling us, I can get anything as negative as I want, which is true. And again, this function just keeps on increasing. It's going to keep on increasing, and so I can get as high a negative value as I want. Again, relationship to our original function, the range of this is what? It's the domain of this function over here. I can plug any value I want into the exponentials, so that means I can get any value out that I want in my log. All right, that's one of them. Now, exponential functions really come in two different flavors. We have the increasing kind here. We also have decreasing exponential functions. A decreasing exponential function, something like this. Give me an example of a decreasing exponential like this. Y equals what? 4 1/2. Okay. Y equals 1/2 to the x is an example of a decreasing exponential function. Remember, decreasing exponential functions are when the base is between 0 and 1. So here's the graph of a decreasing exponential, or right over here. Now I'd like to graph the inverse. What is the inverse of this function going to look like? What is the logarithm expression for the inverse? Y equals base 1/2 x. That's what our inverse function is. That's the inverse of this particular exponential. Now, again, I want to draw the graph. What does the graph of this look like? Well, we start. I'll put in my line y equals x. All right. Now I need to figure out, well, how do I draw this?
Did you change your line because it's a decreasing function?
This line right here?
Yeah.
No, this line is always going to be the same when we're talking about inverses.
Okay.
Our inverses are always reflected across this line y equals x. Okay. So now what does this function look like? Is it going to be an increasing function like that one over there? No. What's it going to look like?
It's gonna start in quadrant 1 and go down to quadrant 4 and go out.
Okay, there you go. So we should get something that looks like this. This is our y equals log base 1/2 of x. Okay. Going through the same process as we did over there, what's the domain of this function? What inputs can I use for log base 1/2 of x? What inputs go in here? Based on the picture of the domain. Inputs. 0 to infinity, right? The domain of this inverse function is not different than the range, not different from the range of our output of our exponential function. Okay? And all exponential functions have the exact same domain. So all logarithm functions must have the exact same domain and range as well. The domain of this particular log function is everything greater than 0. Our range, just like the one over there, negative infinity to infinity. Every logarithm function has the exact same domain and range. Just because I change the base doesn't change the domain and range. They're always going to be the same. So let's do some work with these logarithms real quick. See what we can identify. So just evaluate the following logarithms. And after we do that, we'll look at some of the properties that they have. All right, so the first one, log base 10 of 1,000. Second one, log base square root of 2 of 2. Log base 3 of 1 over 27. Log base 25. 25. Log base log base 2 of 1. All right, so here are 5 logarithms that I'd like you to evaluate to figure out what each one of these represent. All right. Okay, looking at the first one here. Log base 10 of 1,000. What is this asking us? What is another way of looking at this question right here?
10 to the next power equals 1,000.
Right, I'm looking at 10 to some power equals 1,000. How many powers of 10 do I need to get to 1,000? How many? How many? 3. 3 powers of 10 to get to 1,000. Okay? It's early. All right. So log base 10 of 1,000, 3. All right, second one, a little different, but, you know, again, if we interpret it in terms of the exponential stuff, maybe we'll be able to see the relationship. What is this one asking us?
Square root of 2 of the x.
Here we're looking for square root of 2 to some power is equal to 2. What is that one going to do? Down here? Anything? What power? 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 2. There you go. In this case, we square the square root of x. We'll cancel out the square root of 7 to 2. All right, what about the third one here? Log base 3 of 1 over 27. Okay. This one, if we write it up again, we're looking at 3 to some power equals 1 over 27. If you wanted to, another way of writing 1 over 27 is 27 to the negative first. In doing that, you may be able to see the relationship that this is a negative 3. Okay. 3 to the third power gives us the 27. To get the negative exponent then in, gives us the negative 3. What about number 4? Okay, I take my 1/5. 1/5. I have to raise it to some power and get 25 out. Again, if you want to, you can rewrite this as 1 over 25 to the negative first. And then hopefully see the relationship there, x equals negative 2. Okay, and then the bottom one here, log base 2 of 1. What's this one asking?
2 to the 1 power.
Right. Here I'm raising 2 to some power, and I want to get 1 out. This is one of those properties of exponents that we talked about last week. Whenever we take a positive number to this power, we get 1 out.
0.
0 is the power we're looking for in that case. Okay. So when working with logarithms, we have to not only remember some properties of logarithms, we also have to remember some of the properties of exponents as well. Okay. All right, there are 2 additional logarithms that show up frequently. The top one here is an example of one of them. Something called the common log. The common log is, again, just log base 10 of x. And in most